The transformer architecture fundamentally changed how we approach sequence modeling. Today, we'll explore the idea that this powerful mechanism, originally for language, is far more universal.
I remember from case number TCM 12301 that the transformer made sequence modeling parallel. But this paper's title, Attention is All You Need, it sounds so bold.
Before the transformer, almost all state-of-the-art models for things like machine translation relied on recurrent or convolutional networks. Why was that the standard approach?
Those networks excel at processing sequences step by step or finding local patterns. They were the dominant methods for language tasks for years, building context sequentially or through small windows.
The authors state, "We propose a new simple network architecture, the transformer, based solely on attention mechanisms." This was a radical departure from the existing paradigm.
A simple architecture that replaced complex RNNs and CNNs? That must have been quite surprising for the research community at the time.
The key insight was dispensing with recurrence and convolutions entirely. Instead of processing words one after another or with small local filters, it calculates relationships between all words simultaneously.
So it wasn't just adding attention to existing models. It was removing the traditional sequence and spatial processing methods entirely? That's a fundamental shift.
Yes, and this pure attention approach had massive benefits. It was more parallelizable and requiring significantly less time to train. This is what we discussed in case number TCM 15301.
Right, because each word's representation could be computed in parallel with all others instead of waiting for the previous word. That's a huge computational advantage.
Crucially, this new approach didn't just train faster. The paper demonstrates these models to be superior in quality on machine translation tasks, achieving significant blue score improvements. For context, a 2 blue point improvement on these benchmarks is considered very significant, indicating a noticeable leap in translation quality.
Faster and better, those are compelling advantages for any new architecture, explaining its rapid adoption and impact.
This paper showed attention was all you needed for language. But how does this attention-only mechanism actually work to build contextual understanding? Let's break down the intuition.
Let's do it. I'm eager to see how it achieves that superior quality without recurrence or convolutions.
Let's start with a high-level view. Think of the transformer as a single black box. For machine translation, it takes a sentence in one language and outputs its translation.
So I give it bonjour, and it gives me hello. Simple enough for the user, but we know there's a lot happening inside that box.
Exactly. Popping open that box, we see it has an encoding component, a decoding component, and connections between them. This encoder-decoder structure is common in sequence transduction.
So the encoder processes the input sentence, and the decoder generates the output, using what the encoder learned. That part is familiar from other sequence models.
The encoding component is a stack of encoders. Each encoder refines the representation of the input. Think of it like layers of increasing abstraction, each building on the last.
Like a deep convolutional network where early layers find edges and later layers find complex features. Here, the encoders are building deeper linguistic understanding. However, unlike CNNs that operate on local neighborhoods, each transformer encoder layer processes information from the entire sequence, which is a key difference for its contextual understanding.
Inside each encoder is a self-attention layer, a layer that helps the encoder look at other words in the input sentence. This is where the magic of contextual understanding happens.
How does looking at other words work without recurrence? Does it literally scan the whole sentence for every word it processes?
Consider the sentence, "The animal didn't cross the street because it was too tired."
If we're processing it, self-attention helps answer, what does it in this sentence refer to?
A human knows it refers to animal. A simple RNN might struggle with that long-range dependency. How does self-attention resolve this ambiguity in one go?
The model learns to associate it with animal by weighing the importance of all other words when encoding it. It's like each word gets to ask, which other words here are most relevant to me?
So it's not a sequential pass, but a dynamic, weighted connection across the entire input. That sounds powerful for resolving context.
Exactly. While RNNs use a hidden state to carry information forward, self-attention is the method the transformer uses to embed an understanding of other relevant words into the current word.
It's a different way to build context. Instead of a chain, it's a web of connections across the entire sequence. That's a mental model shift right there.
Crucially, the feed-forward layers in each encoder are independent for each word, meaning the various paths can be executed in parallel. This is distinct from the self-attention layer, which does create dependencies.
So the overall transformer processes sequences in parallel, but the self-attention part still requires some interaction between elements. It's not fully independent then.
You're right. While self-attention processes relationships in parallel, it doesn't inherently encode the order of words in a sequence. Without that, the dog bit the man would be indistinguishable from the man bit the dog. So how does the transformer preserve this critical information?
Exactly. If every word's representation is created independently, it loses its place in the sentence. That's a huge problem for understanding meaning.
To reintroduce this vital ordering information, the transformer adds positional encodings to the input embeddings at the bottom of the encoder and decoder stacks. These are unique, fixed patterns of numbers that signal each word's relative or absolute position in the sequence, allowing the model to make use of word order.
So each word gets a position tag added to its meaning vector. The model isn't learning how to sequence, it's just given the sequence information explicitly. That allows it to still process words in parallel.
Precisely. And these encodings are designed so the model can easily learn to attend to relative positions, like the word before me or the word 3 positions away. Now that we understand how it builds context and handles order, let's dive into the core mechanism, how it actually calculates these relevances or associations between words.
How does it quantify relevance? What's the underlying math behind looking at other words?
The self-attention mechanism begins by transforming each word's embedding, let's call it X, into 3 distinct vectors: a query vector, Q, a key vector, K, and a value vector, V. This transformation is done by multiplying X by 3 different learned weight matrices, WQ, WK, and WV. So Q equals XWQ, K equals XWK, V equals XWV.
Query, key, value. This reminds me of database lookups. Does a query vector try to find matching key vectors?
That's a great intuition. The analogy is quite strong. In a database, your query matches keys to retrieve values. Here, a word's query vector searches for relevant key vectors from all other words. The key difference is these are continuous learned vector similarities, not discrete identifiers, allowing for graded relevance. To quantify this compatibility, we then calculate the dot product of the query vector with the key vector of each other word in the sequence.
So a high dot product means the query word is compatible or relevant to that key word. It's like asking, how much does my current word, query, match other words, keys?
After computing these dot products, we divide the scores by 8, which is the square root of the key vector dimension. This is a crucial scaling step.
Why scale them down? Does it prevent some numerical instability or saturation later on?
The annotated transformer confirms this. We call our particular attention scaled dot product attention. The scaling prevents dot products from growing too large, which would push the softmax function into regions with tiny gradients.
So it's not just an arbitrary number, it's directly tied to the vector's dimensionality to maintain stable learning.
Once scaled, we pass the result through a softmax operation. This normalizes the scores, turning them into a probability distribution where all weights are positive and sum to 1.
Now we have our attention weights. Each weight tells us how much to attend to another word in the sentence when creating the current word's new representation.
The final step in calculating self-attention for a word is to multiply each word's value vector by its corresponding softmax score, then sum up the weighted value vectors. This produces the output.
So the value vectors carry the actual content. We use queries and keys to figure out how much to pay attention, and then we blend the content from the value vectors based on those weights.
Putting it all together, the annotated transformer gives us the canonical formula. Attention of QKV equals softmax times QK transpose over the square root of DK times V. This elegantly captures the entire process in matrix form.
This equation is the heart of it. QK transpose is the dot product similarity, scaled, then softmax for weights, and finally applied to V for the weighted sum. That makes sense.
One refinement is multi-head attention allows the model to jointly attend to information from different perspectives. Think of it as having multiple independent subbrains looking at the same input. This isn't literal distinct brains, but computationally, each head learns a unique set of transformation matrices, WQ, WK, and WV, allowing it to focus on different aspects of the input relationships simultaneously. After each head computes its attention output, these are concatenated and then passed through a final linear layer to integrate these diverse perspectives into one refined representation.
Each head learns a different set of Q, K, and V projections, so they can focus on different kinds of relationships, like one head for syntax, another for semantics.
Precisely. Now we have a solid understanding of how self-attention works to build context in language. But the core insight of the transformer is its universality. Can this attention-only mechanism truly see the world, moving beyond text to interpret images? Let's find out.
Images? That seems like a massive leap. How do you even begin to apply something designed for words to something as inherently spatial as a picture, especially without convolutions?
It sounds counterintuitive, doesn't it? Convolutional neural networks, or CNNs, have been the undisputed champions of computer vision for years, designed explicitly to understand local spatial patterns. But the core idea is simple. If the transformer treats language as sequences of words, maybe it can treat images as sequences of something else.
But images aren't sequences. They're grids of pixels with a very strong 2D structure. How do you turn that into a sequence without losing all the spatial relationships?
That's exactly the first step of a vision transformer, or VIT. Instead of processing raw pixels or using convolution filters, a VIT first breaks an image into a sequence of image patches. Imagine taking an image and cutting it into many small, non-overlapping squares, like a jigsaw puzzle.
Okay, so a 224 by 224 image might become 16 by 16 pixel patches. Each patch is then treated like a word. So an image becomes a sentence of visual tokens?
Precisely. After flattening each patch into a vector, we treat these image patches the same way we treat words in a text transformer. each patch embedding becomes an input token for the transformer encoder.
But wait, patches still have spatial relationships to each other. The top left patch is different from the bottom right one. If you just feed them as a sequence, you're losing their original grid position, just like with words in a sentence.
Excellent point. Just like with text, the order of these visual words is crucial. So positional embeddings are added to the patch embeddings to encode their original spatial coordinates. These embeddings tell the transformer where each patch was located in the original image.
So it's the same trick as with words. These positional encodings give the transformer the spatial context it needs, without needing convolutions to explicitly capture neighbor relationships.
Exactly. Once we have the sequence of patch embeddings combined with their positional information, the sequence of patch embeddings now with positional information is then fed into a standard transformer encoder. It's the same architecture we just discussed, applying self-attention to these visual tokens.
And that's it. No convolutions, no fancy image-specific layers, just a standard transformer operating on a flattened sequence of image parts.
That's the radical simplicity and power of it. Vision transformers do away with convolutions entirely, relying solely on the self-attention mechanism to capture long-range dependencies and local feature interactions. Self-attention learns to weigh the relevance of every patch to every other patch, effectively discovering both local and global visual relationships.
So the attention mechanism can learn to look at nearby patches to find edges, or look at distant patches to understand object composition, all dynamically. That's truly general purpose.
It's powerful, but it's not a silver bullet. One key challenge is that VITs often require massive amounts of training data. Without extensive pre-training on huge datasets, training on large datasets is often essential for VITs to achieve competitive performance compared to CNNs on many vision tasks. They also can be more computationally expensive for very high-resolution images because the self-attention calculation scales quadratically with sequence length, meaning the number of patches.
So the parallelization advantage for training is there, but for inference on very large images, the quadratic scaling could be an issue, and they're data hungry. That explains why CNNs are still so prevalent.
Exactly. But despite these challenges, VITs have demonstrated the incredible versatility of the transformer. It's a general sequence processor, capable of handling virtually any data type you can tokenize and linearize. The transformer is truly a matrix of clues that can unlock understanding across domains.
From language to vision, just by changing how you break down the input. It's a profound shift in how we think about neural network architectures.